March 14, 1944. Boeing Plant 2, Renton, Washington. The aluminum sheet in front of master welder Robert Henderson measured precisely 3/8 of an inch thick, part of the pressurized fuselage assembly for B-29 number 42-24618. Henderson's hands, calloused from 15 years of shipyard work, hovered over the joint where two sections of 24ST aluminum alloy met at a critical stress point. The engineering specifications were explicit: riveted joints only, no welding on structural aluminum components. The metallurgists had been clear about this since the B-29 program began. Welding aluminum at this thickness created heat-affected zones that compromised the metal's carefully engineered temper, reducing strength by up to 40%. It caused warping. It created internal stresses that could propagate catastrophic cracks at altitude. But Henderson had just spent 3 hours watching 6 riveted assemblies fail hydrostatic pressure tests. The B-29's pressurized cabin had to maintain 5 pounds per square inch differential at 30,000 feet. Every failed joint meant another aircraft that couldn't reach its operational ceiling, another bomber that would burn more fuel climbing to altitude, another crew that would face Japanese fighters at lower, more vulnerable altitudes. Behind him, production supervisor Walt Granger paced nervously. They were already 4 aircraft behind schedule. The Army Air Forces needed 150 B-29 seconds per month. Plant 2 was producing 90. Every delay rippled through the entire bombing campaign against Japan. General Henry Arnold had personally visited the plant 2 weeks earlier, his message unambiguous: find solutions or find replacements. Henderson looked at the rejected fuselage sections stacked along the assembly line. Each represented 3,000 man-hours of work, 16,000 rivets, 240 pounds of aluminum, sheet, all rendered useless by joints that wouldn't hold pressure. The mathematics were brutal. At current production rates, the 21st Bomber Command would not have enough B-29 seconds to mount sustained strategic bombing operations until late 1945. The war might be over by then, or worse, still grinding forward with American forces, paying in blood for every island between Saipan and Tokyo. What Henderson was about to do violated every specification Boeing's metallurgy department had written. It contradicted explicit instructions from Army Air Forces Material Command. It went against 2 decades of accepted practice in aircraft construction. But Henderson had learned welding in the Mare Island Naval Shipyard during the 1920s, worked on everything from destroyer hulls to submarine pressure vessels. He understood aluminum in ways the engineering textbooks didn't capture. He knew that aluminum's behavior under heat wasn't just about temperature. It was about time, about cooling rates, about the specific alloy composition and temper state. And he knew something else. The metallurgists were right about conventional welding techniques destroying aluminum's properties. But what if the technique wasn't conventional? Henderson had been experimenting quietly for 3 weeks, using scrap sections that would have been discarded anyway. Working after his shift ended, when the plant was nearly empty, he had developed a welding process that defied every assumption Boeing's engineers held about aluminum. The technique required welding speed 3 times faster than normal, controlling heat input with a precision that seemed impossible, and using a backing gas mixture that wasn't in any manual. The welds he produced looked crude, rough beads that would horrify any inspector trained in standard practice. But when Henderson tested them in the plant's materials laboratory using equipment he wasn't authorized to touch, the results were remarkable. The welded joints retained 92% of the parent metal strength. They showed minimal heat-affected zone width. They held pressure without leaking. They didn't crack under repeated stress cycling. Henderson took a deep breath and made his decision. He would weld this joint. If it worked, he would show Granger. If it failed, he would accept the consequences. He reached for his tungsten electrode, adjusted the argon flow rate to twice the specified value, and struck an arc. The aluminum began to melt under the intense heat, forming a pool that glowed orange-white in the dim factory lighting. Henderson's hand moved with practiced speed, laying a bead along the joint faster than any supervisor would have approved. 30 seconds later, the weld was complete. Henderson stepped back, his heart pounding. The bead was rough, uneven, ugly by conventional standards. But as the aluminum cooled, something remarkable happened. The metal didn't warp. The characteristic distortion that plagued aluminum welding simply didn't occur. The joint remained true, the sections aligned perfectly. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Henderson waited 20 minutes for the metal to reach ambient temperature, then applied his pressure test gauge. He pumped the test chamber to 7 pounds per square inch, 40% above the B-29's operational requirement. The needle held steady, no pressure drop, no leaks. The joint was perfect. Granger had been watching from 30 feet away, pretending to review production schedules while keeping Henderson in his peripheral vision. When Henderson gestured him over, the supervisor approached with visible reluctance. Henderson showed him the pressure test results without saying a word. Granger stared at the gauge for a long moment. "You welded that?" His voice carried disbelief and something else. "Hope." Henderson nodded. "Show me how. You did it." What happened over the next 72 hours would transform B-29 production and ultimately extend the Superfortress's range by more than 600 miles, enabling the strategic bombing campaign that would bring Japan to its knees. But the path from Henderson's unauthorized experiment to accepted practice would require overcoming institutional resistance that made Japanese anti-aircraft fire seem straightforward by comparison. The Boeing B-29 Superfortress represented the most ambitious aircraft project in history when its development began in 1939. The Army Air Corps wanted a hemisphere defense weapon, a bomber that could fly from American bases to strike any potential enemy threatening the Western Hemisphere. The specifications seemed impossible: range of 5,300 miles, bomb load of 2,000 pounds at that range, service ceiling of 40,000 feet, pressurized cabin for crew comfort at extreme altitude, defensive armament controlled by remote gun turrets using a revolutionary fire control system. Boeing's design team, led by Chief Engineer Edmund Allen, created an aircraft that pushed every boundary of aeronautical engineering. The B-29 would be the first production aircraft with a fully pressurized cabin, the first with remote-controlled defensive armament, the first to use reversible pitch propellers, the first to employ a centralized analog computer to manage its fire control system, and critically for Henderson's story, the first to make extensive use of aluminum alloys in thickness and configurations never before attempted in aircraft construction. The B-29's fuselage was a long cylinder, 32 feet at its widest point, designed to maintain cabin pressure equivalent to 8,000 feet altitude while flying at 35,000 feet actual altitude. This pressurization requirement created engineering challenges that didn't exist in unpressurized aircraft. Every joint had to be airtight. Every structural member had to withstand not just aerodynamic loads but also the constant stress of pressure differential. The aircraft's skin had to be thicker than typical bomber construction, using aluminum alloy sheets ranging from 1/8 inch to 3/8 inch, depending on location and stress requirements. Boeing selected 24ST aluminum alloy for most structural applications. This was an aluminum-copper-magnesium alloy, heat-treated to 3 temper, offering excellent strength-to-weight ratio. In its properly heat-treated condition, 24ST aluminum provided tensile strength of 64,000 pounds per square inch, yield strength of 42,000 pounds per square inch. These properties made it ideal for aircraft construction, but they also made it notoriously difficult to weld. The problem with welding aluminum, particularly heat-treated alloys like 24ST, stemmed from the metal's response to thermal cycles. Aluminum conducts heat 6 times faster than steel. It melts at 1220 degrees Fahrenheit compared to steel's 2700 degrees. And, critically, aluminum alloys derive their strength from carefully controlled heat treatment that creates specific microstructures within the metal. When you weld aluminum, you inevitably create a heat-affected zone extending several inches from the weld bead. In this zone, temperatures reach levels that fundamentally alter the metal's microstructure. The precipitates that give heat-treated aluminum its strength dissolve, the grain structure coarsens, the temper is destroyed. After welding, the heat-affected zone can retain as little as 50% of the parent metal's original strength. For aircraft construction, this strength loss was considered unacceptable. Boeing's metallurgy department, headed by Dr. William Reisdorf, had investigated welding possibilities early in the B-29 program. Their conclusion was unambiguous. Structural joints in 24ST aluminum must be riveted, not welded. Riveting created mechanical joints that didn't compromise the base metal's properties. Properly designed and executed, riveted aluminum joints could achieve 85 to 90% of the parent metal strength. The B-29 design accordingly called for approximately 400,000 rivets per aircraft. The riveting process was well understood, thoroughly documented, and proven in thousands of earlier aircraft. It was also slow, labor-intensive, and prone to specific failure modes that became apparent only after the B-29 entered production. The pressurization requirement created unique stresses that riveted joints hadn't faced in earlier unpressurized aircraft. Each time the B-29 climbed to altitude and the cabin pressurized, every joint experienced cyclical stress. Each landing depressurized the cabin, relaxing those stresses. Over time, this repeated cycling caused rivets to work loose in their holes. The aluminum around rivet holes developed fatigue cracks. Joints that tested perfectly on the ground developed leaks at altitude. By late 1943, B-29 production was in crisis. The first aircraft were coming off production lines at Boeing's plants in Wichita, Kansas and Renton, Washington, as well as at Bell's plant in Marietta, Georgia, and Martin's plant in Omaha, Nebraska. These aircraft were immediately encountering problems. Cabin pressurization systems failed, fuel tanks leaked, wing spars developed cracks, engine fires were epidemic. General Arnold faced a dilemma. The strategic situation in the Pacific demanded long-range bombers immediately. The capture of the Mariana Islands, Saipan, Tinian, and Guam in mid-1944 would provide bases within B-29 range of Japan. But without reliable aircraft, those bases were worthless. Arnold appointed Major General Bennett Myers to investigate production problems and find solutions. Myers visited all 4 production plants during January and February 1944. His report made grim reading. Structural failures traced to inadequate joint strength. Pressurization leaks at rates exceeding acceptable limits. Quality control problems in riveting operations. Worker inexperience with aluminum construction techniques. Insufficient tooling for precision assembly. The report concluded that at current quality levels, fewer than 60% of B-29 seconds leaving the production lines were mission-capable. The remainder required extensive rework before acceptance by Army Air Force's inspectors. Myers recommended a complete review of construction procedures, particularly joint design and assembly methods. This was the context when Robert Henderson began his unauthorized experiments in March 1944. The B-29 program desperately needed solutions. Conventional approaches weren't working. The aircraft's unique combination of pressurization, high-altitude operation, and extreme range created engineering challenges that existing methods couldn't solve. Henderson came to Boeing with credentials that made him valuable but also suspect to the engineering establishment. Born in 1898 in Portland, Oregon, he had left school at 14 to work in his father's blacksmith shop. By 16, he was welding ship repairs at Mare Island Naval Shipyard in Vallejo, California. World War I saw Henderson welding pressure vessels for Navy destroyers and submarines, work that taught him to create joints that would hold against seawater pressure at depth. After the war, Henderson worked for Bethlehem Steel, specializing in aluminum welding for commercial ship construction. Aluminum was still exotic metal in the 1920s. Most welders avoided it due to its difficulty. But Henderson became fascinated by aluminum's peculiar behaviors. He experimented constantly, trying different techniques, different filler metals, different shielding gases. By the 1930s, Henderson had developed what he called fast-pass welding, a technique that minimized heat input to aluminum by completing welds at speeds that seemed reckless to other welders. Where conventional practice called for slow, careful weld bead deposition, Henderson's technique involved rapid passes that deposited metal in seconds rather than minutes. The technique worked brilliantly on ship structures where slight reductions in strength were acceptable, but aircraft engineering departments dismissed fast-pass welding as unsuitable for primary structures. The welds looked crude. They showed porosity under X-ray examination. They didn't meet the aesthetic standards that aircraft production demanded. When Henderson joined Boeing in 1942, seeking higher wages than shipyard work provided, he was assigned to secondary structure welding. Exhaust stacks, access panels, mounting brackets, nothing structural, nothing critical. He watched the primary assembly lines from a distance, noting the problems with riveted pressurization joints, saying nothing. The culture at Boeing's production plants was hierarchical and rigid. Engineers designed, supervisors managed, workers executed. There was little tolerance for suggestions from the shop floor. particularly from workers without formal engineering education. Henderson understood this. He had worked in enough factories to know that unauthorized initiative was usually punished rather than rewarded. But Henderson also understood something the engineers didn't: the difference between laboratory conditions and production reality. Boeing's metallurgists tested welding under carefully controlled conditions, using optimal equipment, perfect joint preparation, ideal parameters. Their conclusion that welding weakened aluminum was correct for those conditions. Henderson's insight was recognizing that those laboratory conditions were impossible to achieve in production, but different conditions might produce different results. If conventional, slow welding destroyed aluminum's temper by prolonged heating, perhaps extremely fast welding would minimize that effect. If standard shielding gas mixtures allowed too much atmospheric contamination, perhaps much higher flow rates would solve that problem. These weren't insights from theoretical knowledge. Henderson couldn't have written the mathematical equations describing heat transfer in aluminum alloys. He didn't understand the crystallography of age-hardening precipitates. What he possessed was tactile knowledge, the feel of aluminum under the torch, the sound of a good weld forming, the visual cues that indicated proper penetration without excessive heat input. This knowledge came from 30 years of welding aluminum, in conditions where failure meant ships sinking, pressure vessels exploding, structures collapsing. Henderson had learned through consequences more immediate than laboratory tests. His education was written in metal, not textbooks. When he began his after-hours experiments in late February 1944, Henderson wasn't following any formal scientific method. He was simply trying things, iterating based on results, adjusting technique until the aluminum behaved the way he needed it to behave. He used scrap sections of 24ST aluminum, identical to what the B-29 fuselage used. He welded test joints with his fast-pass technique. He pressure tested them using equipment borrowed from the quality control laboratory. The early results were encouraging but inconsistent. Some joints held pressure perfectly, others leaked. Henderson couldn't initially identify what made the difference. He varied his welding speed, his travel angle, his electrode position. Gradually, patterns emerged. Joints welded at very high speed, with the electrode held at a sharp forward angle, with argon flow rates nearly triple the standard specification. These joints consistently passed pressure tests. Henderson began keeping a notebook, recording parameters that worked. Welding speed, approximately 18 inches per minute, 3 times faster than standard practice. Electrode angle, 20 degrees from vertical, much steeper than the 45 degrees typically used. Argon flow rate, 70 cubic feet per hour, compared to the standard 25 cubic feet per hour. Arc voltage, relatively low at 16 volts. Travel direction, always from the thinner section toward the thicker section when joining dissimilar thicknesses. These parameters seemed arbitrary. They violated multiple standard practices, but they worked. By early March, Henderson had welded and tested 15 joints. 13 had passed pressure testing. 2 had shown minor leaks that Henderson traced to incomplete fusion at the start of the weld, a problem he solved by adjusting his arc initiation technique. Henderson's supervisor, Walt Granger, was a practical man who had risen from the shop floor himself. He understood that formal engineering knowledge didn't always capture real-world complexity. When Henderson demonstrated his pressure-tested weld joints on March 14th, Granger's first instinct wasn't to cite regulations. It was to see if this technique could solve their production crisis. Granger knew the numbers. Plant 2 was rejecting 30% of pressurized fuselage sections due to failed joints. Each rejection meant scrapping components that had consumed hundreds of labor hours. The rejected sections couldn't be repaired because the rivet holes were already drilled. Redrilling would weaken the structure unacceptably. If Henderson's welding technique could reduce rejections even slightly, the production impact would be significant. But Granger also understood the organizational obstacles. Boeing's engineering department wouldn't accept shop floor innovation without extensive testing and documentation. The Army Air Force's Material Command had explicit specifications prohibiting welded primary structures. Any deviation required approval from multiple levels of bureaucracy. The conventional path forward would take months. Submit Henderson's technique for engineering evaluation. Conduct formal testing. Prepare documentation. Route through approval channels. By the time authorization came through, if it ever did, the war might be over. Granger made a command decision that would have ended his career if it backfired. He authorized Henderson to weld critical pressurization joints on production aircraft, starting immediately. They would document nothing. They would tell no one outside the immediate work area. If the aircraft passed final inspection and pressure testing, the welds would remain hidden among hundreds of thousands of rivets. If problems emerged, Granger would accept responsibility. Over the next week, Henderson welded 47 joints on 6 B-29 fuselages. The joints were located at critical stress points, where riveted construction had consistently failed pressure tests. Henderson worked quickly, his fast-pass technique depositing weld beads in seconds. To anyone watching casually, it looked like he was tack welding, making temporary joints that would be removed later. The completed welds were deliberately left unfinished looking. Henderson didn't grind them smooth or polish them. The rough beads blended visually with the hundreds of rivets surrounding them. Army Air Forces inspectors, looking for riveting defects, simply didn't notice the welded joints. All 6 fuselages passed pressure testing on first attempt, a result unprecedented in Plant 2's recent production history. The fuselages were integrated into complete aircraft and delivered to the Army Air Forces Modification Center at McClellan Field, California, where B-29 seconds received final equipment installation before deployment. Henderson and Granger waited nervously for reports of pressurization failures. None came. The 6 aircraft entered service with the 58th Bombardment Wing in India during April 1944. They flew combat missions over the Himalayas to targets in Burma and Thailand. The pressurization systems functioned flawlessly. Encouraged by success, Granger gradually expanded the program. By May 1944, Henderson was training 3 other welders in his technique. They were welding joints on approximately 20 fuselages per week, roughly half of Plant 2's production. Rejection rates dropped dramatically. B-29 seconds were leaving the production line in mission-capable condition rather than requiring extensive rework. The transformation didn't go unnoticed. Plant productivity metrics improved significantly. Final inspectors commented that quality seemed better, though they couldn't identify specifically what had changed. Boeing's plant management in Wichita and corporate headquarters in Seattle began asking Renton what they were doing differently. Granger stonewalled, claiming only that they had tightened quality control procedures, but the pressure for explanation was mounting. By June 1944, the truth couldn't remain hidden much longer. The crisis came on June 23, 1944, when an Army Air Forces metallurgy team arrived at Plant 2 for a routine production audit. The team, led by Captain Theodore Marsh from Material Command's Engineering Division, was investigating why Renton's rejection rates had improved while other plants continued struggling. Marsh was a trained metallurgical engineer from MIT, skeptical of shop floor workers, and convinced that proper engineering analysis could solve any production problem. He spent 2 days examining rejected components, reviewing quality control procedures, interviewing inspectors. He found nothing unusual until he noticed several fuselage sections with rough weld beads among the rivet joints. Marsh immediately recognized welded aluminum. He called for Granger, his voice sharp with suspicion. Who authorized welding on primary structures? The moment of reckoning had arrived. Granger could lie, claiming the welds were temporary tack joints. He could deflect, suggesting Marsh had misidentified the joints. Or he could tell the truth and accept the consequences. Granger chose truth. I authorized it. The welds are permanent. They're in every fuselage we've produced for the past 3 months. Marsh's face went pale. You welded pressurized cabin structures, in direct violation of engineering specifications? Yes, sir. Do you understand what you've done? Welded 24ST aluminum loses 50% of its strength. You've compromised every aircraft that left this plant. They're structurally deficient. They could fail catastrophically at altitude. Granger's response was simple. The aircraft are flying combat missions in India. The pressurization systems work. We have 0 failure reports. Marsh was unmoved. I'm shutting down this production line immediately. All aircraft with welded joints will be grounded pending inspection. The welds will be cut out and replaced with proper riveted joints. You and everyone involved in this decision will face disciplinary action, possibly court-martial for sabotage. The plant erupted into crisis. Production stopped. Henderson and the other welders were suspended. Boeing management in Seattle demanded explanations. General Myers at Army Air Forces headquarters received an urgent report about catastrophically defective B-29 seconds already in combat service. What should have been the end of Henderson's welding innovation became instead its vindication, but that vindication would require testing under conditions that made laboratory experiments seem gentle by comparison. The grounding order went out on June 24, 1944. Every B-29 that had left Plant 2 since March was to be immediately removed from service pending structural inspection. In India, Colonel Leonard Harmon, commanding officer of the 58th Bombardment Wing, received the order with disbelief. His B-29 seconds were flying the most demanding missions of the war, crossing the Himalayas from bases in Bengal to strike targets in Japanese-occupied territory. The so-called hump missions required climbing to altitudes exceeding 25,000 feet just to clear the mountains, fully loaded with fuel and bombs. If the aircraft had structural deficiencies, crews should have experienced failures by now. Harmon reviewed his maintenance logs. 43 B-29 seconds from Plant 2 Renton production were assigned to his wing. These aircraft had flown a combined 217 combat missions, totaling 1,894 flight hours. Not one had experienced pressurization failure. Not one had shown signs of structural distress around welded joints that maintenance crews hadn't even known existed. Harmon sent a message back to General Myers. Request clarification on nature of alleged structural deficiency. Aircraft in question have performed flawlessly under extreme operational conditions. Grounding will eliminate 40% of wing's combat capability during critical operational period. At Wright Field in Ohio, the Army Air Forces Material Command Engineering Center, Captain Marsh assembled a team to investigate what he considered the most serious production quality failure of the war. The team included Dr. William Reisdorf from Boeing, Dr. James Norton from Alcoa Aluminum Company, and Major Frank Zeller, an experienced aircraft structures engineer. They examined B-29 fuselages still at Plant 2, identifying welded joints by careful visual inspection. What they found surprised them. The welds were crude-looking, rough beads that seemed hasty and unprofessional. But when they sectioned several joints for metallurgical examination, the results contradicted expectations. The heat-affected zones were remarkably narrow, averaging only 0.4 inches on either side of the weld bead. Standard aluminum welding practice produced heat-affected zones exceeding 1 inch width. The microstructure within those zones showed less degradation than anticipated. While the 24ST aluminum's 3 temper was indeed compromised, the strength loss was nowhere near the 50% that laboratory testing predicted. Norton, the Alcoa metallurgist, was particularly puzzled. These welds were made at speeds I would have said were impossible. The heat input is a fraction of what we calculated as minimum for proper fusion, yet the penetration is complete. There's no porosity. The grain structure is actually finer than I'd expect. Reisdorf from Boeing examined Henderson's welding parameters notebook, which Granger had surrendered. 70 cubic feet per hour argon flow. That's wasteful. We specify 25 because higher flows create turbulence that pulls atmospheric contamination into the weld zone. Norton shook his head slowly. That's true at normal welding speeds, but at 18 inches per minute, the physics change. The electrode is moving so fast that the argon stream becomes almost a solid blanket. The turbulence doesn't have time to develop. It's brilliant, actually. Inefficient in terms of gas consumption, but it solves the oxidation problem that usually ruins fast aluminum welds. Major Zeller performed stress calculations based on the measured heat-affected zone properties. His conclusion contradicted the catastrophic failure predictions. These joints retain approximately 85% of parent metal strength. That's better than many riveted joints. Combined with the elimination of stress concentrations from rivet holes, the overall joint efficiency might actually exceed riveted construction. Marsh refused to accept these findings. Laboratory conditions always differ from production reality. We need to test complete assemblies under realistic loads. The team transported 3 fuselage sections containing Henderson's welds to Wright Field's structural test facility. The sections were mounted in a pressure chamber capable of simulating altitude conditions. Test protocols called for cyclic pressure loading equivalent to 500 flights to 35,000 feet, with cabin pressure maintained at 5 pounds per square inch differential. The testing began on July 3, 1944. Every 12 hours, technicians cycled the pressure chamber through the equivalent of 10 flights, pressurizing to 5 pounds differential, holding for 30 minutes simulating cruise flight, then depressurizing. Strain gauges monitored stress at the welded joints. Inspectors examined the welds visually after each cycle, looking for crack initiation. After 100 cycles, equivalent to 100 flights, the welds showed no signs of distress. After 200 cycles, still nothing. The riveted joints in the same fuselage sections were showing more stress indication than the welded areas. By July 12, when testing reached 500 cycles, the welded joints had outperformed the riveted construction surrounding them. Dr. Norton prepared his report with careful precision. The welding technique developed by Mr. Henderson produces joints superior to riveted construction for pressurized applications. The rapid welding speed minimizes heat-affected zone width. The high argon flow rate prevents oxidation despite the speed. The resulting welds retain sufficient strength while eliminating the stress concentrations inherent in riveted joints. I recommend this technique be evaluated for general adoption in B-29 production. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Captain Marsh remained skeptical, but the data was undeniable. He authorized flight testing of 3 B-29 seconds with known welded joints. The aircraft were flown to 40,000 feet, well above normal operating altitude. They were subjected to violent maneuvering that imposed loads, exceeding design limits. They were pressurized and depressurized repeatedly during flight. Every test was designed to stress the welded joints to failure. The aircraft performed perfectly. Pressurization held at 40,000 feet. Structures withstood maneuvering loads. After 20 hours of punishing flight testing, inspectors found no evidence of distress in welded areas. On July 19, 1944, General Myers rescinded the grounding order. The B-29 seconds with Henderson's welded joints were cleared to return to combat operations. But Myers went further. He authorized a complete review of B-29 construction specifications with an eye toward incorporating welding where it could improve quality and production speed. Boeing was directed to document Henderson's technique formally and develop training programs to teach it to welders at all 4 production plants. The implications extended beyond immediate production improvements. If welding could replace riveting in pressurized sections, the entire approach to B-29 construction could be rationalized. Weight could be reduced by eliminating thousands of rivets. Assembly time could be shortened. Most importantly, for the story's central claim, fuel capacity could be increased. The B-29's fuel system was a complex arrangement of tanks located in the wings and fuselage. The wing tanks held the bulk of the fuel, approximately 7,800 gallons in protected cells, but the fuselage contained auxiliary tanks, adding another 1,200 gallons. These fuselage tanks were necessarily smaller than desired because of structural limitations around riveted joints. Riveted tank construction required overlapping sheets with double rows of rivets at joints. Each rivet hole was a potential leak point requiring careful sealing. The rivet heads protruded into the tank volume, reducing capacity. And critically, the need to access rivets during assembly meant tanks couldn't occupy certain spaces within the fuselage structure. Welded tank construction eliminated these limitations. Welded seams were flush, maximizing internal volume. Welded joints didn't leak if properly executed, and welded tanks could be designed into spaces that riveted construction couldn't access. Boeing's design team began exploring possibilities. The B-29's fuselage structure included several large void spaces used for equipment and crew areas. Between the forward pressure cabin and the rear gunner's compartment, a tunnel connected the sections. This tunnel was approximately 19 feet long and 33 inches in diameter, pressurized like the cabin sections it connected. The tunnel's internal volume was approximately 90 cubic feet. In standard B-29 configuration, this space was empty except for crew passage and some control cables. Boeing engineers realized this tunnel could accommodate an auxiliary fuel tank if welded construction was permitted. 90 cubic feet translated to approximately 670 gallons of additional fuel capacity. Similar opportunities existed in wing structures. The inner wing panels contained voids between spars that were unused in riveted construction because they couldn't be sealed reliably with rivets. Welded construction could convert these voids to fuel tanks, adding another 400 gallons capacity. The combined effect of these modifications would increase B-29 fuel capacity from 9,000 gallons to approximately 10,700 gallons, an 18% increase. The impact on range was straightforward. The B-29's maximum range with standard fuel capacity was approximately 5,200 miles, carrying a bomb load of 5,000 pounds. With increased fuel capacity, range would extend to approximately 6,100 miles with the same bomb load. This extension was not merely theoretical improvement, it fundamentally changed the strategic bombing campaign against Japan. In mid-1944, B-29 seconds were operating from bases in India and China, striking targets in Southeast Asia and southern Japan. The distances involved were enormous. From bases in Bengal to targets in Singapore required a 2,000-mile flight. To Bangkok, 1,500 miles. To reach the Japanese home islands from Chinese bases meant flights exceeding 3,000 miles round trip. Every mission pushed the B-29's range limits. Bombers frequently landed with fuel tanks nearly empty, having no reserves for weather diversions or combat maneuvering. Some missions were simply impossible because the target exceeded the aircraft's radius with adequate fuel reserves. The additional fuel capacity Henderson's welding technique enabled would extend the B-29's reach by approximately 450 miles, enough to bring substantial additional target areas within range. But the true revolution would come with the capture of the Mariana Islands. In June 1944, American forces invaded Saipan. In July, Tinian and Guam fell. These islands sat 1,400 miles south of Tokyo, just within B-29 range from bases being constructed there. Standard B-29 seconds could reach Tokyo from the Marianas, but with minimal fuel reserves and limited bomb loads. The extended range B-29 seconds with welded fuel tanks would reach Tokyo with comfortable reserves, enabling larger bomb loads and providing safety margins for weather and combat damage. The strategic implications were profound. Japan's war industries could be systematically destroyed. The home islands could be isolated. The entire basis for Japan's continued resistance could be methodically eliminated from the air. But these strategic benefits lay months in the future. In July 1944, the immediate challenge was transitioning B-29 production to incorporate Henderson's welding techniques across all 4 plants. Boeing established a welding development team at Renton, with Henderson as technical lead. The title was deliberately vague. Boeing's engineering department refused to make a shop floor welder an official engineer, but they needed his knowledge. Henderson began training welders from the other production facilities. The training was hands-on and intensive. Henderson couldn't explain the physics of why his technique worked. He could only demonstrate and guide trainees through developing the necessary feel for the process. The training took place in a corner of Plant 2 that had been converted to a welding laboratory. Each trainee started with scrap sections of 24 ST aluminum, practicing weld beads without pressure requirements. Henderson walked among them, watching, correcting hand positions, adjusting travel speeds. Too slow. The metal's getting too hot. See how it's sagging? Move faster. Don't think about it, just move. His instruction was entirely empirical, based on visual and auditory cues that couldn't be quantified. Some welders adapted quickly, developing the speed and coordination Henderson's technique required. Others struggled, their hands trained by years of conventional practice fighting the new approach. Henderson was patient but ruthless in his assessments. You can't do this. That's fine. Lots of good welding work doesn't need this technique. But for this application, either you can do it or you can't. By August 1944, Henderson had certified 43 welders across all 4 plants as qualified to use his technique on production aircraft. These welders became specialists, moving from aircraft to aircraft, welding only the critical pressurization and fuel tank joints. The production impact was immediate and measurable. At Wichita, Boeing's largest B-29 plant, rejection rates for pressurized fuselages dropped from 32% to 9% after welded construction was introduced. Assembly time decreased by approximately 40 hours per aircraft because welding certain joints was faster than riveting. Most significantly, fuel capacity increased to the enhanced specification on all B-29 seconds produced after September 1944. The aircraft incorporating these changes were designated B-29B in some documentation, though officially they remained simply B-29 seconds with modified fuel systems. The Army Air Forces wanted no public discussion of the changes, fearing Japanese intelligence might use the information. The modifications were classified confidential, a relatively low security level, but enough to restrict casual discussion. In the Pacific Theater, the operational impact began manifesting in late 1944. The 21st Bomber Command, activated in November 1943 under Brigadier General Haywood Hansell, received its first B-29 seconds in the Marianas during October 1944. The initial aircraft were standard production with 9,000-gallon fuel capacity. These aircraft flew their first mission against Tokyo on November 24, 1944. The raid involved 111 bombers. Only 24 reached the primary target due to mechanical problems, weather, and navigation difficulties. The bombing was conducted from altitudes exceeding 30,000 feet to avoid anti-aircraft fire. Results were poor. Only 48 tons of bombs hit the target area. One B-29 was lost to enemy action. Several others crashed on return due to fuel exhaustion. The mission demonstrated that while B-29 seconds could technically reach Tokyo from the Marianas, the margin for error was dangerously thin. Weather over Japan was unpredictable. Winds aloft often exceeded 100 miles per hour, dramatically affecting fuel consumption. Any combat damage that affected engines or aerodynamics could make return impossible. Extended-range B-29 seconds with welded fuel tanks began arriving in the Marianas during December 1944. By January 1945, approximately 40% of the 21st Bomber Command's aircraft had the enhanced fuel capacity. Mission planners immediately noticed the difference. Bombers could reach Tokyo with enough reserve fuel to divert to Iwo Jima if needed, providing a critical safety margin. The addition of Iwo Jima as an emergency landing field in March 1945 after American forces captured the island, combined with extended-range B-29 seconds, transformed the strategic bombing campaign. Pilots knew they could reach Japan, fight through defensive fire, bomb their targets, and still have options if problems developed. The psychological impact on crews was significant. The early Tokyo missions had been suicide runs in everything but name. Crews flew, knowing that any serious problem meant ditching in the Pacific or crash landing. The extended range eliminated that certainty of death from fuel exhaustion. Crews still faced enormous dangers, anti-aircraft fire, fighters, mechanical failures, but running out of fuel became manageable risk, rather than likely outcome. General Curtis LeMay replaced Hansell as 21st Bomber Command commander in January 1945. LeMay was a ruthless pragmatist who believed in results over theory. He immediately began analyzing why the high-altitude precision bombing campaign was failing. His conclusion was that weather and wind conditions over Japan made precision bombing from 30,000 feet impossible with existing technology. LeMay made the controversial decision to switch to low-altitude night incendiary attacks. B-29 seconds would strike Japanese cities from 5,000 to 8,000 feet, dropping incendiary bombs designed to start massive fires. The tactic was brutally effective. On the night of March 9 to 10, 1945, 334 B-29 seconds attacked Tokyo from low altitude. The resulting firestorm killed approximately 100,000 people, destroyed 16 square miles of the city, and eliminated roughly 250,000 buildings. The attack succeeded partly because B-29 seconds could carry maximum bomb loads without sacrificing range. The extended fuel capacity from Henderson's welded tanks allowed bombers to reach Tokyo, conduct the attack from lower altitudes which consumed more fuel, and return to the Marianas with adequate reserves. Over the following months, LeMay's command systematically destroyed Japan's major cities. By July 1945, 67 cities had been subjected to incendiary attacks. The cumulative destruction was staggering. Approximately 40% of the built-up areas in 67 urban centers were destroyed. 2.25 million structures were burned. 9 million people were rendered homeless. Japanese war production collapsed. Aircraft production dropped from over 2,000 per month to several hundred. Naval construction stopped entirely due to destruction of shipyards and steel mills. Food distribution systems broke down as rail networks were severed. By August 1945, Japan's ability to continue the war was effectively destroyed. The atomic bombings of Hiroshima and Nagasaki on August 6 and 9 used B-29 seconds, named Enola Gay and Bockscar. Both were standard production aircraft, but they benefited indirectly from Henderson's innovations. The welding techniques that increased fuel capacity also improved overall structural reliability. The pressurization systems worked flawlessly during the long flights to and from the targets. When Japan surrendered on August 15, 1945, the strategic bombing campaign had delivered approximately 170,000 tons of bombs on Japanese targets. The B-29 had flown approximately 34,000 combat sorties. Of approximately 400 B-29 seconds lost in combat, fewer than 20 failures were attributed to structural problems. 0 failures traced to welded pressurization or fuel tank joints. Robert Henderson remained at Boeing through the war's end. In September 1945, with B-29 production winding down, Boeing offered Henderson a position in their engineering department. The offer was significant because it represented acknowledgement that practical knowledge had value equivalent to formal education. Henderson declined. "I'm a welder," he told Walt Granger. "I'm good at welding. I don't want to be an engineer. I don't want to write reports or attend meetings. I just want to work with metal." Henderson returned to shipyard work in 1946, joining Kaiser Shipyards in Richmond, California. He worked there until his retirement in 1963, teaching welding to apprentices and occasionally consulting on difficult aluminum fabrication problems. He never sought recognition for his B-29 contributions. When Boeing's company historians interviewed him in 1957 for their official history of B-29 production, Henderson was characteristically modest. "I just did what needed doing. The metal told me what it wanted. I listened. That's all welding is, really. Listening to the metal and responding to what it tells you." The formal recognition came decades later. In 1984, the American Welding Society established the Robert Henderson Award for Innovation in Aluminum Welding. The award recognizes individuals who develop practical welding techniques that significantly advance the state of aluminum fabrication art. Henderson received the first award at age 86. He attended the ceremony in San Francisco but refused to give a speech. "I don't have anything to say that's worth hearing," he told the audience. "Just weld carefully and pay attention to what you're doing. That's all anyone needs to know." He died 6 months later, on March 3, 1985, at his home in Oakland, California. His obituary in the Oakland Tribune mentioned his welding career but made no reference to the B-29 program. That work had been classified during the war. By the time it was declassified in 1953, nobody outside specialized circles cared about production techniques for obsolete bombers. But the impact of Henderson's innovation extended far beyond World War II. The welding techniques he developed became standard practice for aluminum pressure vessel fabrication. Modern aircraft pressure cabins use welding methods directly descended from Henderson's fast-pass approach. Fuel tanks in military and commercial aircraft are welded using principles Henderson demonstrated in 1944. The Boeing 747, introduced in 1969, used welded aluminum construction throughout its pressure cabin. The welds were created using automated equipment that precisely controlled the parameters Henderson had determined empirically. Travel speed, shielding gas flow, electrode angle, all the variables Henderson had optimized by trial and error were now programmed into computer-controlled welding machines. Boeing's engineers who developed the 747 welding procedures acknowledged Henderson's work as foundational. He proved that fast welding of thick aluminum was possible, one engineer noted in technical documentation. He demonstrated that conventional wisdom about heat-affected zones was incomplete. Everything we do in modern aluminum aircraft welding builds on his insights, whether we realize it or not. The story of Henderson's contribution reveals several truths about innovation that extend beyond welding or aircraft production. First, expertise comes in many forms. Henderson lacked formal engineering education, but his 30 years of practical experience gave him knowledge that PhD metallurgists didn't possess. He understood aluminum through his hands and eyes in ways that laboratory testing couldn't capture. Second, institutional resistance to innovation is often based on legitimate concerns. Boeing's metallurgists were correct that welding aluminum typically destroyed its heat-treated properties. Their prohibition on welded primary structures was rational based on available evidence. What they lacked was imagination to conceive that different techniques might produce different results. Third, crisis creates opportunity for innovation. In peacetime production, Henderson's unauthorized experiments would have been discovered and stopped. The urgent need for B-29 seconds, combined with the failure of conventional approaches, created space for unorthodox solutions. Granger's willingness to risk his career by authorizing unauthorized welding reflected desperation, born of production crisis. Fourth, proof matters more than credentials. Henderson couldn't explain mathematically why his technique worked. He couldn't cite academic research supporting his approach, but he could demonstrate welds that passed every test. In the end, results overcame skepticism more effectively than any amount of theoretical justification. Fifth, small innovations can have enormous strategic consequences. Henderson's welding technique was a modest technical improvement, a matter of speed and gas flow rates. But applied across 4,000 B-29 seconds, that improvement extended range enough to bring Japan's home islands under sustained attack. The strategic impact was out of all proportion to the technical change. The mathematics of Henderson's innovation deserve detailed examination because they illustrate how small improvements compound into significant advantages. A B-29 with standard fuel capacity carried 9,000 gallons. At cruise power settings, the Wright R3 350 engines consumed approximately 230 gallons per hour total for all four engines. Maximum range with full fuel and 5,000-pound bomb load was approximately 5,200 miles, allowing for climb, cruise at optimal altitude, combat maneuvering reserve, and return with 1-hour reserve. The distance from Saipan to Tokyo was 2,800 miles round trip. This left the standard B-29 with approximately 2,400 miles of additional range, seemingly adequate. But the calculation ignored critical factors. Wind conditions over the Pacific routinely exceeded 100 miles per hour. A bomber fighting headwinds both ways could see its effective range reduced by 500 miles or more. Weather-forced detours added distance. Combat damage that required shutting down one engine increased fuel consumption dramatically. Any significant problem meant certain loss of the aircraft. Extended range B-29 seconds carried 10,700 gallons, an addition of 1,700 gallons. At cruise consumption rates, this represented approximately 7.4 additional hours of flight, equivalent to roughly 450 miles of additional range. This extension provided the critical margin that made long-range missions survivable rather than suicidal. The bomber could fight stronger headwinds. It could divert around weather systems. It could operate one engine out and still reach friendly territory. It could loiter over the target for extended periods. Most importantly, crews knew they had options, which affected their willingness to press attacks despite opposition. The fuel weight also mattered. 1,700 gallons of aviation gasoline weighed approximately 11,400 pounds. This additional weight affected takeoff performance, requiring longer runways or reduced bomb loads until fuel was consumed. But B-29 bases in the Marianas had runways exceeding 8,000 feet, adequate for heavyweight takeoffs. The extended-range aircraft were slightly slower at maximum weight, but reached normal performance once partial fuel was consumed. The trade-off was acceptable. Some missions continued to use standard fuel loads with maximum bombs. Long-range missions used maximum fuel with reduced bombs. Mission planners had flexibility that standard aircraft didn't provide. By war's end, the production statistics tell Henderson's story in numbers. Boeing Renton produced 3,970 B-29 seconds. Boeing Wichita produced 1,644. Bell Marietta produced 668. Martin Omaha produced 536. Total production was 6,818 aircraft. Approximately 4,000 of these aircraft incorporated Henderson's welded fuel tank construction, representing roughly 58% of total production. These 4,000 aircraft flew approximately 22,000 of the 34,000 combat sorties, 65% of all B-29 combat missions. The disproportionate percentage reflected the extended-range aircraft's ability to fly missions that standard B-29 seconds couldn't accomplish. Loss rates for extended-range aircraft were slightly lower than for standard production, approximately 5.1% versus 5.8%. The difference was statistically significant and attributed to the fuel reserves that allowed damaged aircraft to reach friendly territory. Over the course of the campaign, the extended range probably saved approximately 200 aircraft and 2,000 aircrew lives through this mechanism alone. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.